Right now, a telescope the size of a tennis court is drifting through the darkness a million miles from Earth, catching light that has been traveling for 13.5 billion years. That light left its source when the universe was 2% of its current age. Astronomers decoded it and found something waiting at the very edge of time. A galaxy, bright, massive, and chemically mature, shining from an era when our best models say almost nothing like it should exist yet. So how do you build a galaxy when the universe has barely begun? That question has quietly become one of the biggest problems in astronomy. Not because the discovery is wrong, it has been checked, rechecked, and confirmed with the most rigorous method we have. The problem is time. The universe simply did not seem to have enough of it. And before this video is over, you'll see why the most extreme version of this mystery already collapsed once, why the surviving version is stranger than the headlines, and why a single measurement, a hard ceiling written into the laws of physics, decides whether our entire model of the cosmos survives. To feel the weight of this, you need to feel the timeline. So compress the entire 13.8 billion year history of the universe into a single calendar year. The Big Bang happens at midnight on January 1st. On this calendar, the Sun and Earth don't form until late August. Dinosaurs appear around Christmas. All of recorded human history fits into the final 10 seconds of New Year's Eve. Now ask when the galaxies in this story existed. The answer is the first week of January, some of them within the first 7 days. Astronomers are not looking at the universe's childhood. They are looking at its first morning and finding cities already built. 280 million years sounds like an eternity to a human. Cosmically, it's a rounding error. Our own sun needs about 230 million years to complete a single orbit around the center of the Milky Way. These galaxies were fully assembled within barely more than one galactic lap of the Big Bang. In that sliver of time, the universe supposedly went from a hot, dark fog of hydrogen and helium with no stars anywhere to organized islands of hundreds of millions of suns. That's the mystery. Now let's go back to where it started. Kourou, French Guiana. December 25th, 2021. A European Ariane 5 rocket sits on the launch pad in the morning heat of the South American coast, carrying $10 billion in 25 years of work, folded up inside its nose cone like origami. The James Webb Space Telescope was too big to launch in one piece. Its golden mirror, 6.5 meters across, had to fold. Its sun shield, a 5-layer membrane the size of a tennis court, each layer thinner than a human hair, had to fold. Engineers counted 344 separate single-point failures in the deployment sequence. That phrase has a brutal meaning. If any one of those 344 steps failed, a pin, a latch, a cable, the entire mission was dead. And unlike the Hubble Space Telescope, which astronauts famously repaired in orbit, Webb was headed somewhere no repair crew could follow. Its destination was Lagrange Point 2, a gravitational parking spot 1.5 million kilometers from Earth, 4 times farther than the Moon. If anything jammed out there, there would be no rescue. Thousands of engineers at NASA, the European Space Agency, and the Canadian Space Agency spent 2 weeks in January 2022 watching telemetry screens as the sun shield membranes tensioned one by one, knowing that a single torn layer would turn a generation's work into drifting scrap metal. Every step worked. All 344 of them. Why take that risk? Because of a single physical fact. As the universe expands, it stretches the light traveling through it. Light from the most distant galaxies gets stretched so far that visible light becomes infrared, essentially heat radiation, invisible to the human eye and to telescopes like Hubble. Astronomers measure this stretching with a number called redshift. The higher the redshift, the more the light has been stretched, and the further back in time you're seeing. To catch the first galaxies, you need a giant infrared eye chilled to negative 233 degrees Celsius behind that sun shield so its own warmth doesn't blind it. That is what Webb is, a time machine that runs on cold. Astronomers had a clear prediction for what the time machine would find. Before Webb, the deepest confirmed view of the universe was a Hubble discovery called GNZ11, a galaxy seen about 400 million years after the Big Bang. It was small and faint, and it fit the models reasonably well. The standard picture of cosmology, called lambda cold dark matter, describes a universe where invisible dark matter slowly clumps under gravity, forming scaffolding called halos, and ordinary gas falls into those halos and gradually ignites into stars. Slowly is the key word. Simulations predicted that at 300 or 400 million years after the Big Bang, Webb would find galaxies that were tiny, dim, and rare, faint embers at the edge of night. In July 2022, the first deep field images came down from Lagrange Point 2, and astronomers started scanning them for the reddest, most stretched objects they could find. The embers were bonfires. Survey programs with names like Sears and Glass began flagging candidate galaxies at enormous estimated distances, and there were far too many of them, and they were far too bright. One team calculated that some early candidates were 10 to 100 times more luminous than the models predicted for their era. Within weeks, the phrase started circulating in headlines and even in the titles of scientific papers. Impossibly early galaxies, galaxies that shouldn't exist. But before you accept that framing, you need to know how those first distances were measured, because this is where the story nearly went off the rails. Those early estimates used a technique called photometric redshift. In plain language, astronomers photograph a galaxy through several colored filters and estimate its distance from which colors are missing. Ancient hydrogen gas absorbs all light beyond a specific cutoff. So a galaxy that vanishes in blue filters but glows in red ones is probably extremely far away. Probably. Because there's a trap. A relatively nearby galaxy choked with dust or filled with old red stars can mimic the exact same color signature. And in 2022, the trap snapped shut on one of the most famous candidates in the world. A galaxy called Sears 93316 made global news with an estimated redshift of around 16, which would have placed it just 230 million years after the Big Bang. Then astronomers pointed Webb's spectrograph at it, the instrument that splits light into a detailed barcode of wavelengths instead of a handful of colors. The barcode didn't lie. The galaxy sat at redshift 4.9, still distant, still ancient by human standards, but billions of years later than advertised. A dusty imposter whose colors had perfectly faked the signature of cosmic dawn. That embarrassment changed the rules of the entire field. From that point forward, nothing counted until spectroscopy confirmed it. Without the barcode, a candidate stayed a candidate. Keep that standard in mind because everything that follows survived it. While that debate raged, a second and even more alarming claim landed. In February 2023, a team led by astronomer Ivo Labbé published 6 candidate galaxies from the Sears survey field in the journal Nature. These weren't record breakers for distance. They sat 500 to 700 million years after the Big Bang. The alarming part was their estimated weight. Some appeared to contain tens of billions of solar masses in stars, roughly rivaling the modern Milky Way, which had 13 billion years to grow. The researchers themselves nicknamed them universe breakers. If those masses were real, the math turned ugly fast. Galaxies that heavy, that early, would have needed to convert nearly 100% of their available gas into stars, essentially instantly. Nothing in astrophysics works at 100% efficiency. In our local universe, galaxies typically manage around 10% or less. So by early 2023, the mystery had 2 heads, too bright and possibly too heavy. One of those heads was about to be confirmed beyond doubt. The other was about to be quietly cut off. And the order in which that happened changes what this whole mystery actually means. Start with the confirmation. Throughout 2023, a deep survey called JADES, the James Webb Advanced Deep Extragalactic Survey, began pointing Webb's spectrograph at the most promising candidates in a patch of southern sky. First came JADES GSZ 13.0, spectroscopically confirmed at redshift 13.2, about 320 million years after the Big Bang. A real galaxy, verified by the barcode, earlier than anything Hubble ever touched. The record held for about a year. Then, in January 2024, the spectrograph locked onto a source that had been bothering the team since early 2023, an object that looked too big and too bright to be real. The instrument stared at it for almost 10 hours. When the data was processed, the spectrum showed the unmistakable hydrogen cutoff at redshift 14.32. The galaxy was named JADES GSZ 14.0, and it existed just 290 million years after the Big Bang. One team member later admitted that when the confirmation appeared on his screen, he stood up from his computer and laughed because the result felt ridiculous. I mean, think about what that spectrum implied. The galaxy spans about 1,600 light-years, and its size settled a crucial question. A single feeding supermassive black hole can blaze with deceptive brightness, but it shines from a point, not from a 1,600 light-year expanse. This light was starlight. Hundreds of millions of solar masses of young stars, blazing across a region big enough to resolve at a time when simulations said such an object should have been vanishingly unlikely to appear in a search area that small. The too bright problem was no longer a candidate. It was a confirmed feature of our universe, and then the chemistry made it worse. Follow-up observations with Webb's mid-infrared instrument detected the signature of oxygen glowing inside JADES GSZ 14.0. That detail matters more than any distance record. The Big Bang produced only hydrogen, helium, and a trace of lithium. Every atom of oxygen in existence was forged inside a massive star, and released when that star exploded. Massive stars live fast, a few million years, but you still need a full cycle. Stars ignite, burn out, detonate, and seed the gas, and then a new generation forms from the enriched debris. Finding abundant oxygen at 290 million years means this galaxy wasn't a first draft. Entire generations of stars had already lived and died inside it. The universe's first morning, and the recycling program was already running. And the compression problem doesn't stop with stars. Remember GNZ11, Hubble's old record holder, the galaxy that once fit the models so comfortably? When Webb's spectrograph revisited it, astronomers found the fingerprints of a feeding supermassive black hole in its core, weighing over 1 million times the mass of our Sun, just 430 million years after the Big Bang. Black holes grow by swallowing gas, and swallowing has a natural speed limit because the infalling material glows so fiercely that its own radiation pushes new food away. Growing 1 million solar mass black hole that early strains that speed limit badly. So the early universe wasn't just building stars faster than expected. It was apparently growing monsters faster than expected too. Every clock astronomers checked was running fast. If this timeline is starting to feel impossibly compressed to you, that's the correct reaction. And it's exactly the feeling driving hundreds of research papers right now. Now, for the head of the mystery that got cut off, because this is the honest part of the story, those 6 universe breakers, the Milky Way mass monsters from February 2023, they largely dissolved under scrutiny. When spectroscopy and longer wavelength data arrived, the most extreme object in the sample turned out to be dominated not by an impossible pile of stars, but by a growing supermassive black hole, its glowing disk of infalling gas masquerading as the light of billions of suns. Estimated masses across the sample dropped substantially, and that object belonged to a whole new population Webb kept finding, compact crimson points astronomers nicknamed little red dots. They are tiny, often just a few hundred light years across. They glow with a strange split personality of blue and red light, and once astronomers knew what to look for, they turned up scattered across nearly every deep field Webb has taken. Nothing like them exists in the nearby universe. Stranger still, when X-ray telescopes stared at them, expecting the telltale glare that feeding black holes normally produce, they found almost nothing. That silence pushed theorists toward an exotic idea now gaining traction. Some little red dots may be so-called black hole stars, entire star-like envelopes of dense gas swaddling a feeding black hole, muffling its X-rays while glowing with borrowed power. Whatever they turn out to be, the lesson for our mystery is the same. Once you accept that black holes can impersonate the light of massive stellar populations, the truly universe-breaking weight estimates deflate. Galaxies exceeding the theoretical mass limit, in the words of one follow-up study, turned out to be unlikely at any point in Webb's data. So here's the problem, stated precisely, with the hype stripped away. The standard model of cosmology predicts how many dark matter halos of each size should exist at each moment in cosmic history. Webb has not broken that prediction. The halos are there on schedule. What Webb broke is a much more specific assumption: how efficiently and how visibly the gas inside those early halos turned into stars. The confirmed early galaxies are not too numerous to exist and not too heavy to exist. They are too bright, too soon. The universe didn't build impossible structures. It built permitted structures at a speed and with a brilliance nobody expected. Cosmology isn't broken. Its opening chapter is being rewritten, and that rewrite has 3 leading suspects, each of which changes something real about how we understand the first stars. Suspect 1 is bursty star formation. In today's universe, when a cluster of new stars ignites, their radiation and stellar winds blast the surrounding gas apart, choking off further starbirth. Feedback, astronomers call it, a built-in speed limit. But the early universe was a different environment. Gas clouds were vastly denser, and some models show that in clouds that dense, gravity wins the race. The gas collapses into stars faster than feedback can disperse it, producing violent, feedback-free bursts, where a galaxy converts gas into stars at many times the modern efficiency, flares brilliantly for a few million years, then goes dim. If early galaxies strobe like this, Webb's deep fields naturally catch the ones caught mid-flash, making the whole population look brighter than its true average. Suspect 2 is dust, or rather its absence. In the nearby universe, star-forming galaxies are shrouded in soot-like dust that swallows ultraviolet light. Models assumed the early universe would be similar, but several confirmed early galaxies, Jade's GSZ 14-0 among them, show remarkably little dust reddening. Perhaps those violent starbursts blew the dust out of the galaxy entirely, leaving the young stars naked and glaring. Removed the assumed sunglasses from the models, and predicted brightness jumps without adding a single extra star. By the way, if you're enjoying how deep this rabbit hole goes, subscribe, because the edge of the observable universe keeps moving, and the next confirmed record could drop any month. There are 2 suspects left, and the next one is the strangest of them all. Suspect 3 touches the nature of the first stars themselves. Astronomers describe a stellar population by its initial mass function, the recipe of how many big and small stars form from a collapsing cloud. In our galaxy, small red stars vastly outnumber giants, but the first star-forming clouds contained no heavy elements to help them cool and fragment, and warmer gas tends to collapse into bigger pieces. Many theorists suspect the early recipe was top-heavy, producing far more brilliant giant stars per ton of gas. Taken to its extreme, this idea points at a legendary missing population. Astronomers call them Population 3 stars, the hypothetical very first generation, forged from completely pristine gas. Models suggest some could have reached hundreds of times the mass of our Sun, burning blue-white and furious for only a couple of million years before detonating. No telescope has ever caught one directly. But if the earliest galaxies were seeded with even a modest share of these giants, their collective glare alone could explain a large slice of the surplus brightness Webb keeps finding. A single hot giant can outshine 10,000 suns. Shift the recipe toward giants, and a modest galaxy suddenly blazes like a massive one, tricking us into overestimating everything. And there is a quieter 4th suspect that isn't the universe at all. It's our bookkeeping. A young galaxy's gas can blaze with intense emission lines, narrow spikes of light from glowing oxygen and hydrogen, and in broad filter photographs, those spikes can masquerade as the steady glow of an established stellar population, inflating mass estimates. On top of that, Webb's deep fields cover almost comically small patches of sky, so a survey that happens to hit an unusually crowded pocket of the early universe can make rare objects look routine. Statisticians call it cosmic variance. Detectives would call it a witness with a limited view. The real answer is probably a blend of all 4, and untangling them is now a central project of extragalactic astronomy. But notice something about all 4 suspects. Not one of them requires new physics. Not one of them touches dark matter, dark energy, or the expansion of the universe, which raises the question this entire debate ultimately hangs on. What result would actually break cosmology? Because, to be clear, cosmology already lives with genuine tensions. And the most famous is the Hubble tension, a stubborn disagreement between 2 ways of measuring how fast the universe expands today. But tensions like that are arguments about precision, 2 careful measurements missing each other by a few percent. The early galaxy problem offers something rarer and cleaner, a binary test with a hard line that either gets crossed or doesn't. The line works like a tripwire. Every dark matter halo comes with a strict allowance of normal matter, the protons and neutrons that stars are made of, roughly 16% of the halo's total mass. That fraction was measured independently in the afterglow of the Big Bang itself, the cosmic microwave background. It is one of the most solid numbers in all of science. So each halo has a hard ceiling. Even at a physically absurd 100% efficiency, a galaxy cannot contain more stellar mass than its halo's baryon allowance. Find one single spectroscopically confirmed galaxy that clearly exceeds that ceiling for the biggest halo possible at its epoch, and the standard model of cosmology genuinely fails. That is the tripwire. 4 years of Webb data, hundreds of confirmed early galaxies, and the wire has never been touched. Several objects have strolled uncomfortably close to it, demanding efficiencies of 50% or more, which is why theorists are sweating. But close is the whole story so far. Strained, not snapped. Which brings the story back to the present, because the frontier moved again. In April 2025, a team led by MIT astronomer Rohan Naidu pointed Webb at a candidate from a survey called Mirage or Miracle, and the spectrograph confirmed a new champion. MOMZ-14, at redshift 14.44, seen just 280 million years after the Big Bang. The result passed peer review and was formally published in January 2026 in the Open Journal of Astrophysics. And once again, the galaxy refused to behave. It is remarkably luminous, so unexpected that the discovery paper literally carries the phrase "a cosmic miracle" in its title. Naidu put it plainly: humanity is now seeing farther back than ever before. And in his words, it looks nothing like what was predicted. But MOMZ-14 hides a clue the previous record holders didn't offer. Its light carries a strong signature of nitrogen, a chemical fingerprint that closely resembles something surprisingly familiar: the ancient globular clusters orbiting our own Milky Way, dense balls of stars that rank among the oldest objects in the nearby universe. Sitting 280 million years after the Big Bang is an object whose chemistry rhymes with fossils in our own backyard. And it isn't alone. GNZ11, the galaxy hiding that early black hole, shows a similar nitrogen-rich fingerprint, which suggests this strange chemistry wasn't a fluke, but a signature of how the first dense star clusters were built. That's a thread connecting the first galaxies to the oldest surviving stars around us, and it hints that whatever exotic recipe cooked the early universe, traces of it may still be orbiting over our heads tonight. So this is where we stand in the summer of 2026, a growing chasm, as one researcher described it, between theory and observation at cosmic dawn. Not a broken model, a model whose first chapter keeps getting outpaced by its own telescope, and the decisive test is already sitting in a clean room. The Nancy Grace Roman Space Telescope, NASA's next great observatory, is now fully assembled and could launch as soon as late 2026. Roman sees a swath of sky 100 times wider than Webb's narrow keyhole. Webb found these impossible-seeming galaxies in patches of sky smaller than a grain of rice held at arm's length. Roman will survey continents of sky. If ultra-bright galaxies at cosmic dawn are rare statistical flukes, Roman's wide net will prove it. If they are everywhere, the textbooks on the first billion years get rewritten for good, and Webb itself is far from finished. Its launch was so precise that it saved enough fuel to operate for 2 decades. And astronomers are now aiming it through massive galaxy clusters, using their gravity as natural magnifying lenses to reach objects even Webb couldn't see alone. Either way, we are months from the answer starting to arrive. And Webb may break its own record yet again before Roman even leaves the ground. Think about what this whole saga actually means. Humanity folded a cathedral of gold and capped it into a rocket, threw it 1.5 million kilometers into the dark, unfolded it through 344 chances to fail, and aimed it at the first morning of time. We expected embers. We found bonfires. We expected a slow, hesitant dawn and found the sky already burning. And the honest scientific response was not to declare the universe broken, but to admit that the universe's first act was more ambitious than our imagination. Every atom of oxygen in your lungs, every atom of iron in your blood, came from that same frantic early stagecraft. Stars igniting, dying, and seeding the dark, generation after generation, starting far sooner and burning far brighter than anyone dared to model. The universe, it turns out, was in a hurry. It could not wait to make stars. It could not wait to make oxygen and carbon, and eventually, us. And 13.5 billion years later, some of that first desperate light finally landed on a cold, golden mirror, built by the descendants of those elements, who looked at the first morning of the universe and realized the lights were already on. The universe was in a hurry. Now we finally get to find out why. If you want to be here when Roman's first wide-field images drop, or when Webb breaks redshift 15, subscribe and turn on notifications, because the edge of the observable universe has moved 4 times in 4 years, and it is about to move again.